Hey, financial modeling guys. So what I'm going to do today, I'm going to actually make it a little bit for myself, not for you. I'm going to record this video for me and not for you. And what I'm going to do now, I'm going to derive the Black-Scholes PDE. So what is this Black-Scholes PDE? Okay, that's a fundamental PDE of risk management, and that's a PDE that basically governs, governs the behavior of all the securities that are derivative of some sort, of a stock or a bond or any other derivative, right? So when we speak about derivative, we speak about an instrument whose payoff is dependent on the underlying security. So for example, an option depends on the underlying security. So remember that the payoff of the option at the strike price, at the maturity, is something like that, right? So if you have an option, you have the basically the option, but not the obligation to buy it at a certain strike price. So if it's more than this strike price, you will buy it. If let's say your strike is 25 and the stock is 50, by the end of maturity, you will make 25 bucks, right? However, if it's less, right, you will not buy it. Now, this is different from futures where you are obliged to do that. You're obliged to buy it. Here you are not obliged to buy it. You have the option. And that's actually very, very different animal. It's becoming much, much more interesting. Now, the Black-Scholes formula, what the Black-Scholes PDE now, controls basically all, right, the options. So we are going to do, so we are going to look on V, which is the value of the option. It's going to be a function of the strike price, of the stock price, not strike price, but stock price, and time t. So time t is when we start to count now until maturity, which is big time t. What we are interested to know is how to price this baby. Now, when we want to price it, we want, of course, to price the expected value. We do not want to price, right, the random component. We want to price the expected value of this thing, right? So how to do it? Okay. So what we want to do, the first thing we want to do, right, is to use the Ito's lemma. So the idea is that if we know the price at the end, okay, we can, do in a way backward induction, right? You did it with trees. So if you know the price here, you can discount back and get prices here and then go back until the end. What we are going to do now, right, is actually going to be something very similar. But we are going to do it in a continuous fashion, not in a tree-based fashion, which is basically a discrete fashion. Okay? So what we are going to do now, we are going to start by looking on dV, okay, which is going to be the change in the price when the stock moves, okay? So we know Ito's lemma, right? And we know that this is going to be delta V to delta S times ds plus delta V to delta T times dt plus half delta square V to delta S square ds square. Now we know, okay, that ds divided by s, right, equals to mu dt plus sigma dw. Okay. That's a fundamental, that's our fundamental equation. What this equation says to us, okay, that the return, okay, is randomly distributed with per unit time, with per unit movement of mu dt plus this guy, which is its volatility, sigma dw. Okay? So basically what we say, right, that returns are actually random walks because we have this, but it also has a drift. Okay? And the drift is always positive. So now let's apply this guy to this guy. What are we going to get? We're going to get the dV equals to delta V divided by delta S times S times mu dt plus sigma dw plus delta v to delta t times dt. We cannot do anything with that, okay? Plus, and now we're going to get the following thing here, right? We're going to square it. We're going to look on ds divided by s squared, which is going to be basically, you know, mu square dt square plus mu sigma t dt dw plus sigma square dw square, which is this one is dt, right? So the usual way that we're doing it all the time, we're going to say that this is going to be s square times sigma square times dt. Okay? So until here, right, it is just Ito's lemma. Now, what are we going to do with it? Well, now comes a trick, a very nice trick, okay? What we are going to do now, we are going to eliminate randomness. Right? How we are going to eliminate randomness? Well, we are going to set up a portfolio, okay, which is basically going to be an option plus a share of a stock. Now, if you eliminate the randomness, okay, you know exactly how this portfolio is going to behave. Because all portfolios that do not have randomness will earn a risk-free rate. Because it's just going to be like cash, right? So let's say you have basically 20 bucks, right? And you know that it's 20 bucks. What can you do with it? The only thing that you can do with it is to put it into a bank account, okay? In this setup. So if you eliminate randomness, right, you are going to have a portfolio without any randomness, and you will know exactly how much it is going to be earned. Now, how do you eliminate randomness? Well, that's the trick. The trick here, right, is to consider a portfolio which actually will kill this guy. How do you kill this guy? Well, it's actually easy peasy, right? You can look on a portfolio where you are going to get basically, you know, your V minus delta V to delta S times S. Now, this is a little tricky because this guy is a number. Okay? So what you are going to do now, you are going to consider this portfolio. V is your value of the option, which you don't know. This guy you quote-unquote don't know, but you know this. Okay? Now, what is going to be the change in this portfolio? Well, we can calculate. Okay? So it's going to be dV minus delta V to delta S times ds. Why delta V to delta S? Because delta V to delta S, right, is a constant number. We know what it is. It's basically, you know, the sensitivity of the option price, right, to the movement of the stock. If you want, it's actually very close to the beta, right? But the beta operates on percentages. This guy operates on dollars. So if you move this guy by $1, the V, right, will move by delta V to delta S times this $1. Just like with durations. Very similar concept to duration. So now, what is this? Well, this is actually easy peasy because you know this formula. So you are going to get that this is delta V to delta S times S mu dt plus delta V to delta S times S sigma dw, okay, plus delta V to delta T times dt, plus, and now we're going to get S squared times sigma squared times dt, and minus, right? Now I'm going to get this. So what is this? This is delta V to delta S times mu S times mu minus delta V to delta S times S times sigma dw. Okay? This is coming from the following equation. We know that ds divided by s equals to mu dt plus sigma dw. So it means that ds equals to s times mu times dt plus sigma times s times dw. Okay? Now, what do we get here? Well, that's actually becoming extremely interesting. As Humphrey, no, it was Damon. Damon said to us it was really cool. Okay? So what's happening here? Well, and of course we have dt's here. Of course I'm forgetting. So first of all, this guy and this guy goes away. What else goes away? This guy and this guy goes away. So what is left? Right? What is left? So what is left is as follows. Delta V to delta S, okay, times, let's see. Okay, so delta V to delta S is gone actually. So what is left is as follows, right? So first of all, delta V to delta T times dt plus s square times sigma square times dt. This is what is left for this portfolio. Only this guy and this guy are left. Now, on the other hand, what this portfolio is going to earn? This portfolio is going to earn the risk-free rate, right? So it means that if I look now, so this is dV. But however, if I look on this guy, it is going to be R times V minus delta V to delta S times S times dt. Why dt? Well, because if I'm going to take this guy, this portfolio, right? It's cash. It's like cash, right? It has no random component. So it's basically like $20 or something, right? What will you do with it? You have to put it into the bank. How much it is going to earn per unit of time? Per unit of time, it is going to earn the risk-free rate times dt. We're talking about earning here. We're talking about actual dollars, okay? The actual dollars here are equal. So now, right, so this goes away. We're getting the following equation, delta V to delta T plus S square times sigma square. Of course, I forgot the half here somewhere. It should be half here, right? Because in the e to the lemma it's half. Plus delta V to delta S times S minus RV equals 0. This is a Black-Scholes formula. Right? So this is basically the Black-Scholes PD. Now, watch. First of all, you do not see any mu here, right? The mu got eliminated. Why the mu got eliminated? This is actually a very interesting thing. Because in reality, how do you guys are going to hedge this? What you are going to hedge, you are not going to use, because you are here, you want to hedge in the future, right? You are not going to use the actual stock. You are actually going to use the futures. And futures, ladies and gentlemen, right, have only one price. It's S times e to the RT, right? It's the fair price of the future. So when you hedge with futures, you're forced to agree, right, that everything has to grow with the risk-free rate. Because everything has to grow with the risk-free rate, you will not see the growth of the stock here. In other words, the growth of the stock itself has nothing to do with the price of the underlying options. This is actually a very interesting conclusion because this is actually extremely counterintuitive. Extremely counterintuitive. Okay? Now, if you have something like that, right, the other things that you want to observe, that you have basically a time component here, which means, right, that the derivative the derivative actually depends on time. But if it's a perpetual option or a perpetual bond or any perpetual instrument, this guy goes away and you are actually getting equation only in S. What does it mean? It means that if you have a perpetual option, and we're going to talk maybe about perpetual options maybe in the next video, okay? If you have a perpetual option, let's say perpetual put, okay, the time component is gone, because if you are here or you are here, you start to count, it's infinite maturity. Has nothing to do, right? Has nothing to do with the time that you started. Here, right, the time component is here because, you know, if you reach maturity, the option expires. But assume that the option didn't expire. It went until infinity, right? So if you are here, if you start here at this time, or you start here, or you start here, it doesn't matter, okay? So here, because of that, this delta V to delta T, okay, is basically incorporates the fact that you have basically a time component here, and this actually makes it very, very, very tricky. It's much easier, and maybe I'll show it to you in the next video or a couple of videos of how to deal with options, right? And this was actually the first example where the option was priced, because people do not know it, but it was a very interesting story that the first option that was priced by Merchant's teacher, Per Paul Samuelson, and he actually considered an equation like this without the delta V to delta T. And then it's actually very easy because it's just a you know, it's an equation of the second order. It's actually has a very straightforward solution. Okay? So this was the first video that I'm going to record on this. I'm going to now record another video. Thank you and have a great day.